So welcome back to the online workshop on black holes, BPS, BMS, and Integrability. This afternoon, we have just one talk by Max Zimmett from Harvard University. So feel free to ask questions, keep yourself unmuted, and then if you want to ask a question, keep yourself muted, and then if you want to ask a question, unmute yourself. So please, Max, go ahead.
Okay, great. Thank you very much for the invitation. And just to reiterate, I think we're all getting more used to Zoom talks, but I can't really see you. So please interrupt and ask questions whenever you have them. Okay, let me get started. As you could see, my talk will be about K3 metrics. So Claude-Biot compactification has played a central role in string theory. And this is, of course, because of its relationship with low energy supersymmetry. Type 2 compactifications preserve 4D n equals 2 supersymmetry and are the natural setting for studying mirror symmetry. And then heterotic and orientifold compactifications have been used for semi-realistic starting points for string phenomenology. And Claude-Biot compactification more broadly is the setting in which much of our non-perturbative understanding of string theory has been developed. So K3 has played a particularly important role because it's a four-dimensional Claude-Biot manifold, four real dimensional. And it's in a sense the simplest non-trivial Claude-Biot manifold, by which I mean it's the only Claude-Biot manifold in dimension 4 or fewer, which is compact but not a torus. There's this accidental isomorphism, which means that two complex dimensional Claude-Biot manifold is automatically hyperkähler. So that might be one way of thinking about why there's so few examples of Claude-Biot manifolds in 4 dimensions. And a concrete way to think about K3, which will be useful in this talk, is you take an orbifold of a torus, and then you resolve the fixed points of that orbifold action. So since K3 is hyperkähler, it preserves even more supersymmetry than a typical Claude-Biot manifold. So for example, if I want to make this into a threefold by multiplying with a T2, then this has 4D n equals 4 supersymmetry. And so again, this plays a central role in string duality because this has the same amount of supersymmetry as heterotic string theory, just on a torus. So heterotic type 2 duality plays an essential role in our understanding of how the various perturbative superstrings are related. The earliest example of black hole microstate counting was in string theory was performed using K3. So historically, K3 has played a central role in string theory. And remarkably, all of this was achieved without an explicit form of the metric. And indeed, no smooth, compact, non-toroidal Ritchie-flat Claude-Biot metric is known, or I should say was known before our work. That's what I'm going to tell you about. Why might this matter to a string theorist? Supposedly, one of the first things we see in string theory courses is the nonlinear sigma model action. So we learn that tree level string vacuums, string vacua are we can construct them from conformal field theories, such as a nonlinear sigma model. But in reality, because we don't have the metric, this formulation is not very useful. And for K3, this is particularly well motivated because the beta function is exactly 0, not just at leading order in alpha prime. So as an example of our ignorance, even for K3, which, as I said, has been under intense study for decades now, the world sheet partition function is known almost nowhere in moduli space. So today I'm going to describe for you some two different constructions of explicit K3 metrics based on recent work with Shamit Khatri and Arnav Tripathi. And one of these constructions are I'll call it the Coulomb branch construction, is not yet entirely explicit. That there's some discrete data that needs to be determined in order to make it completely explicit. So I'll flesh that out more. The other construction, the Higgs branch construction, is completely explicit, and there's a very useful, computationally useful perturbative scheme for constructing this metric at all orders in perturbation theory. And so so this first section, I will introduce the Coulomb branch formalism, then I'll introduce the Higgs branch formalism. Then here I'll relate those two formalisms at first order in this perturbative scheme. So by proceeding to all orders in perturbation theory, then we expect to be able to by comparing these two formalisms, we should be able to read off all of the discrete data that we need in order to flesh out the Coulomb branch construction. So then we'll have two completely independent explicit constructions. Okay, so let me, that's my outline. Let me get started. So let me just introduce what a little string theory is. That's the physical context for studying our first construction. We're going to be using a particular little string theory, so let me just focus on this example. Heterotic small instanton 5 branes are the heterotic string theory version of NS 5 branes. So you know their tension diverges as 1 over G string squared. That they have a decoupling limit, by which I mean that you can take G string to 0, the bulk dynamics turns off, but nevertheless the dynamics on the 5 branes remains interacting. And from the supergravity perspective, this works because the corresponding soliton is so singular. So an infinite throat with G string diverging down the throat develops. So no matter, you can set G string to 0 at infinity, but nevertheless, G string will diverge as you approach the core of the soliton. And this little string theory, it's not gravitational, but it's not a quantum field theory either. And one way to see this is that it has T-duality, so there's no unique stress energy tensor. The way it sees geometry is not unique. Okay, and we're going to be interested in studying the moduli space of this little string theory compactified on T2 and on T3. So I need a way to differentiate between those two setups. So I'll call one the 4D theory and one the 3D theory, even though they're both 6-dimensional. So I'll just be counting their non-compact dimensions. Okay, so there's a very nice way to understand what the moduli space of these of this little string theory is. So first, let's study the moduli space of the theory on T2. So we can use strong weak duality, and that takes us to a D5 brane wrapping T2 in type 1 string theory. And now to study the moduli space of the theory on T2, we can just use T-duality twice to replace the D3 brane by a D5 brane, sorry, the D5 brane by a D3 brane, probing T2 mod Z2 now because of the rules for how orientifolds work. But at a general point in moduli space, there are quantum corrections that smooth out this T2 mod Z2 to a more general F-theory compactification on CP1 with some elliptic fibration describing the spatially varying axiodilaton, and the total space of that fibration is a K3 surface. So the natural way to describe the moduli space of this D3 brane is by thinking of this as an F-theory compactification, where the D3 brane is probing K3. So of course the moduli space is just the CP1 because the elliptic fiber directions are sort of fake, but they'll play a role in once we go down to 3 dimensions.
So a question?
Yes.
So you said that, I mean, in the heterotic picture, there's some decoupling limit that you mentioned earlier. So here also there's some corresponding decoupling limit one has to take?
That's right. Yeah.
What is it?
So in the heterotic string theory, the string coupling is going to 0. So over here, what that means is that the volume of the CP1 is going to 0, which is important because the normal decoupling limit one takes for studying world volume theories is you study energies much smaller than the string scale. But here, if the K3 is bigger than the string scale, then you're not going to be able to probe the whole K3 surface, and you'll just see a non-compact little piece of it. So that limit is important in this duality frame also, in order to be able to see the whole K3 surface.
Thanks.
Yeah, and in fact, that's what differentiates the little string theory from you can take low energy limits and get various gauge theories out of this little string theory, but the moduli space of these gauge theories will always only ever see a non-compact little piece of the K3 surface. So that's why it's important to start with the K3 surface. Okay, so we can perform the same exercise to study the three-dimensional moduli space. So we again have a D5 brane wrapping T3 in type 1. We T-dualize 3 times now to get a D2 brane, probing T3 mod Z2 orientifold. And now the non-perturbative description is provided by M theory. So the extra dimension is provided by the M theory circle, and this is a way from the probe D2 brane point of view to understand heterotic M theory duality. So over here we have a 5 brane wrapping T3, and here we have an M2 brane probing the K3 surface. So again, the moduli space is now the whole K3 surface, not just the CP1, whereas in 4 dimensions it was just the CP1.
Sorry, and again the decoupling limit is the same as before here?
Yeah, it's now the volume of the whole K3 surface goes to 0.
I see. Mm-hmm.
So the relative volume of the base and fiber is still an interesting modulus, but the overall volume is going to 0. So in terms of the Narine moduli space, the moduli space factors as some double coset times R plus, where R plus in the heterotic frame is just the G string. So the moduli space here is of Ritchie flat metrics on K3. So again, that's some double coset times R plus, where R plus is just the volume. So we just kill off the R plus factor. Okay, and so this is familiar from all of the constructions of world volume gauge theories and string theory. The moduli of the big string theory become parameters of the little string theory. They're not dynamical. And similarly, the gauge symmetry in space-time descends to global symmetry of the little string theory. So the 4-dimensional theory, we have the usual, the Narine lattice is gamma 18,2, the self-dual even lattice of signature 18,2. So that means that you get a 20-dimensional gauge symmetry in space-time, which means you'll have a rank 20 gauge symmetry in spacetime, which means you'll have a rank 20 global symmetry in the little string theory. That's in 4 dimensions. And then, once you compactify on a circle, you have 19.3. So you get a 22-dimensional global symmetry. Okay, so our strategy is going to be to compactify the little string theory on T3 to get a K3 as a moduli space. But this little string theory is some strongly coupled non-perturbative theory. So we need a perturbative parameter in which we can expand in order to give some analytic formulas for the metric. So what we're going to do is we're going to pick out one of the circles as being much bigger than the other 2 circles. So we'll compactify first on a 2 torus, and then further compactify on a very large circle compared to both the little string length as well as to the T2. So I'll call the radius of this big circle R. So the R goes to infinity limit. We're just going to recover the moduli space of the probe D3 brane in F theory, and the metric there is the usual metric on the base of K3 in an F theory compactification, which was written down by in this paper in 1990. And that metric is Ritchie flat, but it's singular at the various singular fibers. So the purpose of the Coulomb branch perspective is to construct a corrected metric, which is approximately the same as this semi-flat metric away from the singular fibers, but which gets huge corrections near the singular fibers, which makes it smooth. So the corrections away from that limit are just determined by instantons in the theory, which are associated to the world lines of four-dimensional BPS particles, which are wrapping this large circle. And so the if I have a BPS particle of mass m, then the action of that instanton is exponentially small in the mass, and so in the radius. Sorry. And so for any whenever I have a massive BPS particle, its contribution to the metric will be exponentially small. But near singular fibers, we get some massless BPS states. And so their contributions will not be exponentially suppressed no matter how large you make R. So this is a physical way of understanding the order of magnitude of various contributions to the metric. In particular, it means that there's a sort of obvious physical approximation that will be very accurate, which is you only keep around the BPS states which become massless somewhere, because any BPS state that is always massive, its contributions will always be exponentially suppressed. Okay, so I should say that the honest way to solve this problem is to use the instanton calculus. That is a very difficult approach, which is far beyond our means at the moment. One reason for that is we don't even know the counts of these BPS particles. That's going to be a main focus of this talk. But even if one knew the counts of those BPS particles, determining their contributions to the metric requires going through the very calculated instanton calculus, and you need to do some very complicated calculations in perturbation theory with instanton background. So we're going to use a different approach due to Gaido-Moore-Knightsky, which exploits holomorphy.
Sorry, Max.
Yeah.
Boris speaking. Is it correct that this metric of Vafa Chaparral is a CMAP metric with a certain prepotential describing the metric on P1? That's
right. Yeah, this is the usual. This obeys the usual formalism of rigid special Kähler geometry.
So could you write down the explicit prepotential on which this construction is based?
Yeah, I don't think so. Prepotentials are only locally well defined. So it's easier to write down the function defining the elliptic fibration, which is if I call my modulus on the base of this the P1A, then I have some function tau of A, which defines the spatially varying axiodilaton defining that elliptic fibration. And so that's one derivative of the prepotential, and that's maybe nicer to work with for K3.
Okay.
But yeah, that function is very well known. You just invert the J function applied to some polynomial.
Mm-hmm. Thanks.
Okay, so let me give a one-slide review of this formalism due to Gaido-Moore-Knightsky. The idea is that there are certain very nice canonical holomorphic functions on K3. Well, okay, their formalism was developed in the context of 4D equals 2 field theories. So we pointed out that this formalism generalizes to K3 with only small modifications, which I'll explain in a second. So let me just review the formalism first. There are some very nice holomorphic functions on this moduli space. Here, zeta labels which complex structure we're talking about, because K3 is hyperkähler. There's a whole CP1 worth of complex structures. So you get some canonical function in every complex structure. Gamma here is labels a charge in the charge lattice of the four-dimensional theory. And by charge lattice, what I mean is the at low energies, we're familiar with from Seiberg-Witten theory that you get some abelian gauge theory. And so I'm talking about the charge lattice of that abelian gauge theory. So there's some electric and magnetic charge, and then there are a whole bunch of flavor charges. So for every charge, you get a canonical function, and physically what this function is it's just a supersymmetric Wilson-Tooft line with that charge describing a heavy probe particle with that charge whose world line is wrapping the very large circle. So that gives you so you take the expectation value of that Wilson line in this theory, and that defines some holomorphic function on the moduli space. The reason it's holomorphic is just by virtue of supersymmetry. This BPS observable is guaranteed to be holomorphic. And the reason these are nice is that, first of all, they're holomorphic functions on K3. So you know that I must be lying to you because K3 is compact, and so it doesn't have holomorphic functions. And the way around that is that they're only piecewise holomorphic. They're discontinuous at certain places due to wall crossing phenomena. And furthermore, we know they're asymptotics just by various limits. And that turns out to be enough to completely characterize these functions. We know they're holomorphic functions with certain discontinuities and certain asymptotic behavior. That tells you that these functions satisfy this integral equation. And at sufficiently large R, Gaida-Mornitsky show that this has a unique solution, which characterizes these functions. And it's not just an existence theorem. They can actually construct the function. And the way this works is you start with some 0th order function, which I'll call the semi-flat function. You plug that in on the right-hand side, evaluate this right-hand side, you get some first order approximation. Then you plug the first order approximation back in and you get a second order approximation, and you can keep iterating that ad infinitum, and that procedure will converge at sufficiently large R. And you know, the first 0th order approximation was already exponentially good everywhere away from the singular fibers. And so iterating this very rapidly converges because you're only making exponentially suppressed changes away from the singular fibers. And near the singular fibers, for example, for generic fibers, the first approximation is already extremely good. Or more generally for IN singular fibers, the first approximation is already very good at the singular fibers as well. Okay, so here very explicitly is with the form of these semi-flat semi-flat functions. So Z gamma here is the central charge function from Seiberg-Witten theory. Yeah, that's and theta gamma here is a Wilson-Tooft line. You know, these are the fancier supersymmetrized versions of Wilson-Tooft lines. These are just honest Wilson-Tooft lines. So again here, gamma contains both gauge and flavor components. So what I mean by a flavor contribution to a central charge is just a complex mass parameter. These are the mass parameters that contribute to four-dimensional physics. And then the gauge Z gamma is those are just, you know, A and A dual. Those are the usual periods, the coordinates on the moduli space of the four-dimensional theory. And then similarly here, these are the new coordinates and mass parameters that we get when we compactify from 4 dimensions to 3 dimensions. So the flavor theta gammas are some new real mass parameters, and the gauge theta gammas are some new coordinates on the torus fibers of the moduli space. And then given these canonical functions, you plug them in, you get this canonical 2 form, whose Laurent expansion is very simple. It just has these 3 terms, and those 3 terms just are the 3 Kähler forms, omega I, omega j, and omega k. that completely characterize everything you would want to know about the hyperkähler geometry. So for example, the metric you just get by matrix multiplication. And similarly, you get the complex structures from matrix multiplication. So that's the Gaudium-Warnitsky formalism in one slide. And the only real modification that one gets when one upgrades to little string theory, besides the fact that the base is now compact, is that in the normal Gaudium-Warnitsky formalism, real mass parameters don't affect the semi-flat limit at all. Whereas once you upgrade to the little string theory, we showed that certain real mass parameters upgrade your semi-flat limit from a elliptic fibration to a more general genus 1 fibration. So that doesn't have a section. But otherwise, all the formulas work the exact same way. Okay, so this is just the punchline of what I just said. At large R, these functions take some universal form up to exponentially suppressed corrections. Oh, I should mention these omegas here, omega of gamma, those play, that's the data that we have yet to determine. These are some integers, which are the BPS index of the little string theory compactified on T2. So those determine the discontinuities of these functions X. And so that's how they show up in this formalism. So we've reduced this differential geometry problem to a BPS state counting problem. We just need to know these integers, and then we plug them into this formalism, and we'll get the metric. I should mention that because of wall crossing phenomena, they depend on where in the 4D moduli space, where on that CP1 one is. So one has some piecewise constant lists of integers that you plug them into this formalism, and you'll get some K3 metrics. And thanks to the wall crossing formula in principle, one only needs to determine them at one point in parameter and moduli space, and then they're determined everywhere. In practice, this might not be such a useful way to specify this data. So it might be better to just write down to determine the whole spectrum everywhere, if that's possible, which it should be. Okay, so as I mentioned, just iterating that integral equation once already gives you a very accurate approximation for generic configurations. So this is just what that approximation looks like. I don't want to unpackage all of this notation, but this is some Bessel function, which is exponentially suppressed at large values of its argument. So you can see the exponential suppression in the mass of some BPS states times R that I promised you earlier. Okay, and there's a very nice geometric picture for what these BPS states look like. That was developed in the context of 4D n equals 2 field theory back in the 90s, which is, if you go back to the F theory picture of a D3 brane probing K3, then think of this circle, this dark circle, as the D3 brane, and these are some 7 branes in this F theory compactification. Then the BPS states just correspond to string webs, which start on the D3 brane and then terminate on 7 branes. And these string webs are particularly nice at points in moduli space with constant tau. Tau is the complex structure of the elliptic fiber, because that means by the formulas of special geometry that the base is flat. And so this is just some combinatorial flat surface problem. It's a very hard combinatorial flat surface problem because the base is compact, but at least in principle, one has some very nice combinatorial flat surface problem. So just to emphasize the logic, this formalism applies for general K3 surfaces near the semi-flat limit. One can specialize to these loci with constant tau, and things simplify a bit because the BPS state counting problem is particularly nice. We're going to specialize even more to limits which are orbifold limits. So tau is not only constant, but we have this product T2F times T2B mod C ZQ. So F is for fiber, B is for base. So we think of this as a T2F vibration over T2B mod ZQ, which is topologically the same as CP1. And so you know, as I've been saying, the non-abelian global symmetry comes in this little string theory, comes from coincident 7 branes in this F theory picture. And moving the D3 brane probe close to one of the 7 brane stacks and taking the low energy limit yields a super conformal field theory, either SU2NF equals 4 or E6, E7, or E8, one of the Minahan and Mashansky theories. So I've encoded the lists of singular fibers in these orbifold compactifications in this table. So for T4 mod Z2, you just get 4 SU2NF equals 4 singular fibers. And then for these other cases, you get some other singular fibers. So here you have 3 E6 CFTs. Here you have 2 E7 CFTs and 1 SU2NF equals 4 CFT. And then the rest, so I remember the rank of the gauge group of heterotic on T2 is always 20. So that means the rank of the global symmetry group of the little string theory on T2 is always 20. So that's just made up for by some U1s. And then the last 2 columns here just emphasize that the complex structure of T2F and T2B is fixed at some values. So, you know, the first third root of unity in these 2 cases, or I in this case, whereas for T4 mod Z2, you can have any complex structures that you like. So the BPS structure spectra of the CFTs that I just mentioned differ significantly from the BPS spectrum of the little string theory. And you can see that in this picture. So what I've pictured here is the Q equals 2 case of this slide. So this is the whole T2 base. And so really only the left half of this picture is physical because of the Z2 quotient. So here's my D3 brane, and here's an example of a string web in this theory. So it starts here and then it branches off and ends on 2 different singular fibers. And so you can see that because of the compactness of the base, or the presence of multiple singular fibers, the BPS spectra here will look very different than in the CFT. In the CFT, the only BPS states I get correspond to straight lines going from my D3 brane to one of the singular fibers. So I can have BPS states going from here to here, or here to here, or here to here, or here to, you know, I can wind around and then end on some 7 brane. So you get a bunch of infinite towers of CFT spectra as a subspectrum of the little string theory spectrum. But in addition, you get a bunch of other BPS states. Now I mentioned the existence of those abelian global symmetries on the last slide. We know from n equals 2 supersymmetry that the mass of BPS states is the absolute value of the central charge. And so, and we know that the mass of these string webs has to be increasing based on how many times I wind around before ending on my various branes. And so that tells you that those abelian global symmetries must be associated to conservation of F1 and D1 winding about the 2 1 cycles of this T2. Because you need some contribution to this central charge function coming from winding. Okay, so our strategy will be to, in 4 dimensions, we're going to specialize to the orbifold point in order to have a very nice BPS spectrum, but we still want to study smooth K3 metrics, not just orbifold metrics. So we're going to turn on arbitrary Wilson lines for the 4D global symmetry as we reduce on S1R in order to smooth out the orbifold. So those are those theta sub gamma Fs, those real mass parameters I mentioned. We'll turn on arbitrary values of those. And so then the contributions to that first approximation coming from the BPS states of the little string theory with gauge and global charges of some arbitrary flavor charge, but then you have some primitive gauge charge, which I call gamma G, times some imprimitivity, some integer, some positive integer M. The contributions from all of those states takes this nice form. Okay, and then as I mentioned, there are a whole bunch of CFT spectra, which are subspectra of the big little string theory spectra. And those have a particularly nice form. The reason for that is because their winding charges, remember those strings are just, what it means to have imprimitivity M is just that you're M copies of the same string, stretching from a D3 brain to a single singular fiber. And so the winding charges are also given by M times some primitive winding charge. And so if we...
Sorry, a question.
Yeah.
This is Sergey. Can you precise what is your charge lattice?
Yeah, the charge lattice is gamma 18,2 plus Z2. So the Z2 is the electric magnetic charges, and then the flavor lattice is the usual lattice from Norine compactification on T2.
And for example, in this formula, can one recognize these components? So they are...
Yeah, so the gauge charges gamma G are valued in Z2.
Uh-huh.
Then the rest of that 20-dimensional lattice is made up by, so for, let's just focus on the Q equals 2 orbifold for concreteness. So there the charge lattice just is 4 copies of the spin 8 weight lattice, plus an extra Z to the 4 for the U1 to the 4 global symmetry.
Okay, thanks.
And these formula are only valid at the first order in instant-on approximation. Is that correct?
That's right. Yeah. So this is both restricting to first order in the instant-on approximation and also only keeping around the effects of those simplest string webs. Okay, so the point I want to get from this slide is just this last line here. There are these nice functions encoded in K3 metrics, which encode the BPS spectra of these TFTs. And you know, the whole BPS spectra of the little string theories are actually encoded in these metrics also. But we're as I mentioned before, we're gonna do some perturbation theory, which here we'll explain how to get the metrics to all orders, but then when we compare the two formalisms, we'll only work at first order just for simplicity. In future work, we'll move to all orders. And at first order in perturbation theory, we're only going to see these simplest string webs. So far, we can only study the CFT BPS spectra, but more generally, we'll be able to study the whole little string theory BPS spectra. Okay, so that's everything I have to say about the this Coulomb branch formalism. So let me mention before I move on that provides in addition to the intrinsic interest in K3 metrics, this provides a second reason to be interested in K3 metrics because they encode the answer to these BPS state counting problems. So there's some cool enumerative and representation theoretic information encoded inside of these K3 metrics. Okay, so now I'm going to move on to a completely different formalism, but it's physically related, as I'll say it in this slide.
Sorry, can I ask you again a question before we move forward?
Yeah.
From what you said, it seems like the charge lattice can change when you go from when you move in the modular space. So am I wrong?
That's right. So it changes both as you move in parameter space and in moduli space. So as one moves in moduli space, this is the usual phenomenon in Seiberg-Witten theory where the charge lattice is fibered non-trivially over the moduli space. And as one moves in mass space, this is the fact that the global symmetry is getting Higgsed down to various subgroups, and then it gets re-enhanced to various enhanced gauge symmetries, enhanced global symmetries at various points in the Norine moduli space.
but then, since the charge lattice changes, also the BPS spectrum will change drastically. So, is it true that then the standard wall crossing is not enough to describe all changes in the BPS spectrum, because there are these also changes of the essentially of the labels of the BPS indices? Yeah.
The lattice changes smoothly. So I mean, it's always a rank 20 lattice. So what I mean by the lattice changes is really that Narayan compactification gives you a natural metric on the flavor part of the lattice, and that's what's changing. But as just a freely generated abelian group, it's always z to the 20. So in that sense, it's not changing. So the usual wall crossing formalism does apply. Because the wall crossing formalism doesn't care about this Narayan metric on the lattice. It cares about the symplectic pairing, but that varies perfectly nicely.
Okay, so you say that if you find, let's say, these BPS indices at some point in the modular space, and then you apply wall crossing formulas, it's enough to cover the whole modular space.
That's right.
Okay, thanks.
Okay, so let me move on to this other formalism. So in this other approach, K3 arises as a Higgs branch of some D2 brane theories rather than as a Coulomb branch. So we're going to just have a D2 brane probing the T4 mod ZQ orbifold. And because of a non-renormalization theorem, there are no quantum corrections to this Higgs branch. I should stress this is we have a perturbative type 2A string vacuum. So there's no non-abelian gauge symmetry. So this is not just the S1 reduction of the earlier M3 frame on K3 that we mentioned earlier. The way that these differ, as Aspinwall explained, is there's some discrete B field on the two cycles of this orbifold. And from the D2 brane point of view, this B field breaks some global symmetries. So the non-abelian global symmetries are broken down by this B field to just the U1 to the 20th. But nevertheless, even though this is a different vacuum, G string is in a background vector multiplet, and that discrete B field dilutes away and the G string goes to infinity limit. And so the moduli space is the same as that of the M2 brane we were just talking about. This picture of two theories, one Coulomb branch, one Higgs branch, their moduli spaces agree, and the global symmetries are different in the UV. This is reminiscent of 3D mirror symmetry, and this is not an accident. This is the same picture. This is a similar picture that was used by Perotti and Zaffaroni to yield the simplest mirror pairs. So this is sort of an analog of 3D mirror symmetry for little string theories. Okay, so the formalism that one uses to describe Higgs branch moduli spaces is familiar, so I'll cover this pretty quickly. The superpotential takes this form trace of phi mu plus, where phi is the chiral multiplet in the n=4 vector multiplet, whose vev vanishes on the Higgs branch. So the equation of motion you get from the superpotential just comes from differentiating with respect to phi, and you just get mu plus equals 0. So that's the F-term equation, where mu plus is called the complex moment map. It's a function of the hypermultiplets. And then the D terms analogously take the form mu r equals 0, where mu r is some Hermitian function of the hypermultiplets. So that's the real moment map. And then the Higgs branch, you just set the potential to 0. So mu r equals mu plus equals to 0. And then you quotient by the gauge group. And that will give us a K3 surface. So just as a warm up, very quickly, SimN C2 you can get from n parallel D2 branes. And so that's some 3D n=8 gauge theory. We restrict to the Higgs branch, so that means that we're going to arbitrarily take all of the scalars in the vector multiplet to vanish. Then the complex moment map is this commutator. The real moment map is this commutator, where U and V are the two chiral multiplets in the adjoint hypermultiplet. And then you can this quick argument shows you that indeed the moduli space is SimN C2. Okay, so then we can upgrade to our first orbifold. Our orbifold, our D2 branes probing an orbifold. The formalism explained by Douglas and Moore is you start on the C2 covering space with a D2 brane and its image, and you impose some orbifold projections on the world volume theory of that D2 brane. So the starting point is the n equals 2 theory from the last slide, so 2 parallel D2 branes, and then you just require that your chiral multiplets satisfy these conditions, these Z2 conditions, and that furthermore, gauge transformations are the only gauge transformations you keep are those which satisfy this equation. So you just figure out the most general solution of those constraints, and then they take these forms, and then you plug these things back into the real and complex moment maps, and quotient by the gauge symmetry, and you indeed get C2 mod Z2. That works. Okay, so now let's study the same idea, but now we're gonna have an infinite dimensional gauge group in order to get T4. So this will be our first compact example, and this idea was studied by Waddy Taylor. So now we have infinity to the 4 image branes. We have a whole lattice of image branes, but we impose this z to the 4 orbifold projection. So u and v are my complex coordinates on C2. So we have some lattice lambda, which is isomorphic to z to the 4, and nu and nv are the complex coordinates of some lattice vector in lambda. So we just orbifold by these translations. So the gauge group that survives these orbifold projections is just, I call it U1 hat. It's the maps from the dual torus to U1. This is just saying that we have U1 gauge theory on the dual torus. And that is actually what you could have expected from T-duality, because a D2 brane probing T4 is the same as a D6 brane wrapping the dual torus. And so it makes sense that you get a U1 gauge theory on the dual torus. And the hypermultiplets U and V that satisfy these orbifold projections, they just define a U1 connection on the dual torus. So if I introduce complex coordinates psi1 and psi2 on the dual torus, then the matrix elements of U and V, these are some big infinite dimensional matrices, but I can just think of them as being the Fourier modes of a connection, a U1 connection on the dual torus. So E of n here is just the exponential written in complex coordinates, and it's also sometimes useful to work with real coordinates. So you can write that as e to the I n dot y. Okay, so that was a bit quick, but any questions about that? We're just studying some U1 gauge theory on the dual torus. Okay, and the moment map equations taken together just tell you that the connection, the curvature, the field strength of that connection is self-dual. So we're just looking at, is anti-self-dual. So we're just looking at the moduli space of anti-self-dual connections, mod gauge equivalence. This familiar calculation tells you that anti-self-dual connections on this trivial bundle are actually flat. And so we're just studying the moduli space of flat U1 connections on the dual torus, which is indeed the original torus. So, Wilson, this is the usual correspondence in T-duality, where the moduli space of the D6 brane wrapping the dual torus is just given by its Wilson lines. And compactness of this moduli space is due to large gauge transformations. Okay, so we can finally get to K3. So we're going to realize K3 as the resolution of this orbifold. So we're going to orbifold C2 by a lattice Z to the 4 again, and then by ZQ, or equivalently by this semi-direct product. And so what this means in practice is you start with a U of Q gauge theory on the dual torus, and then you impose some ZQ projections on the gauge fields and on the gauge transformations that you're allowed to have. So remember, B here is the U of Q gauge field that is constructed out of U and V. And the moment map equations now look almost identical to before. The only catch, the only new ingredient is we have these terms, which are some, these are the blow up parameters that resolve the orbifold. And they're just some delta functions which are localized at the fixed points of the ZQ action. So what one learns is that K3 is a hyperkähler quotient of this infinite dimensional flat space of ZQ equivariant SUQ connections on the dual torus with prescribed singular boundary conditions by the group of equivariant SUQ gauge transformations. And you can count the number of triples of Fi parameters that show up in this equation. So they're triples because you know, if I move this to the other side, then this is clearly, this side is self-dual. So clearly this needs to be self-dual. So etas here are just some constant coefficient self-dual tensors on two tensors on two forms on the dual torus, and there are three of those. So you get to pick three of these guys for at each fixed point. And then you know, I here runs from 1 to q minus 1. So if you count the number of Fi parameters you get, you'll get the right number of moduli for q equals 2 and q equals 3. And then 4 and 6 have some extra identifications amongst these etas. They're not all totally independent. And that just comes from the requirement of ZQ equivariance again. So the point is that not all of the fixed points in those two compactifications are, so like, let me just focus on Z4 for concreteness. Some of the points have Z4 stabilizers, but some only have Z2 stabilizers. And so the Z2 stabilized points get identified with each other. And so you get some relationships coming from that. Okay, so then we can see that the moduli space is indeed the orbifold I claimed by we first the moment maps plus gauge transformations, or equivalently Kaluza-Klein masses, let you restrict to 0 modes. So our connection is just constant. And then you study the 0 mode moment maps and gauge transformations, and those let you write the 0 modes of the connection. Remember the Fourier modes U0 and V0 are just a single complex number U times this matrix and a single complex number V times this matrix. So the U and V are going to be our coordinates on the K3 moduli space. And then certain large-ish gauge transformations, in a sense I don't want to talk about, preserve our gauge choice, and they implement the quotient of U and V by that lattice. So you indeed get all of the identifications you need, and you get this orbifold T4 mod ZQ. Okay, so now let me very quickly explain our perturbative scheme for correcting the orbifold metric to a smooth K3 metric. So now we're going to just take the most general possible 0 modes, U0 and V0, that satisfy the orbifold constraints. And we're going to write them as this orbifold value, which we saw on the last slide, plus a correction which is orthogonal to the orbifold value. And then our goal is to solve for the general nth Fourier mode, all Fourier modes, as a function of those coordinates U and V that we're going to use on our moduli space. So we're going to define an embedding of K3 into this infinite dimensional flat space. Yeah. So the idea is, suppose inductively that you know some nu minus 1th order approximations. Then you write the next order approximation as just what you already knew plus some correction. Plug those in, and you find that the moment map equations are linear in these corrections, even though the full moment map equations are nonlinear. And furthermore, the moment map equations mix all of the Fourier modes with each other. But at this linear order, they completely decouple into finite-sized chunks, which are not so big. And then there's a natural gauge choice which shares those features. This is, basically non-abelian version of Coulomb gauge. And so very explicitly, these are the moment map equations that we get at each order. And again, they're just linear in these corrections. And here's the gauge fixing condition we're imposing, which is linear. So we're just solving these linear equations at every order. And furthermore, the coefficients on the right-hand side don't depend on what order you're working at. And so, you invert the same matrix at every order, and the only thing that changes is this vector of constants over here is constructed out of the lower order terms that you already found. So explicitly, you just construct these new effective FI parameters at the nth order by summing over all of the lower order terms that you already found. So this recursive procedure allows you to write down the metric completely. And so here I just solved that linear equation. I don't want to unpackage all of this, but the point of flashing the slide here is just that it's extremely explicit and simple. This is just some finite sum. We plug this into Mathematica, and this is very simple to implement. One cool feature of this solution is that if you sum up the contribution from each nu, so you get the exact all orders expression, then what you find on the right-hand side is okay, this looks a little gross, but this is just an integral equation that U and V have to satisfy. On an integral equation on the dual torus. So I wrote this here in momentum space, so it's not clear that this is an integral, but yeah, this is just a simple integral equation on the dual torus. And this will prove, okay. So this is some interesting formal analogy with the Gaudium-Warnitsky formalism, but there are some big differences also. They have infinitely many different integrals that they have to compute over various rays in the complex plane associated to all of the BPS states, whereas we just have these integrals on the dual torus. So there are some formal similarities, but also some big differences. Okay, and then once you have these embeddings, once you've solved for the Fourier modes as a function of U and V, then you just plug these into these these scalar forms on this flat infinite dimensional space. And so you'll get dun is of this form, and same for dvn. You plug them in, and that gives you the exact metric on K3. So you just pull back these scalar forms on the flat infinite dimensional flat space to K3. Okay, so this is the form of the corrections. I don't really want to say this. So this is the first order corrections that you get. We plugged these into Mathematica and verified that the metric that you get from that is Ricci flat, that the complex structures square to -1 like they have to. Okay, great. Okay, so now as promised, with the remaining time I have, let me compare the Higgs and Coulomb formalisms with each other. And now we're just going to restrict to first order and perturbation theory. So what we're going to do is take these formulas that we wrote here at first order and perturbation theory, and we're going to Poisson resum them over the lattice parametrized by NV. So this is the part of the lattice associated to T2F, the fiber direction. And what Poisson resummation is, in case you don't remember, is just you start with this identity and multiply both sides by some function f of x, and take the and then integrate over x. So what the left-hand side becomes is just the sum over that function evaluated at all of the lattice points, and on the right-hand side you get the Fourier transform of that function evaluated at a bunch of lattice points. Yeah, okay. So I'll spare you all the algebra, and this is the answer you get, which looks extremely similar to this expression I wrote. Hopefully this is the right slide. Okay, the hyperlinks are broken. Whatever. Yeah, so this looks the same as the expression I promised you we would find earlier. So in particular, the geometry of string webs winding around is encoded in this lattice of winding charges and in the flavor central charges that are showing up here. And so the hyperkähler quotient formalism actually knows about the geometry of all these string webs, and it knows about the counts of these BPS states in the form of these functions that show up here. So at first order in perturbation theory, we found that the functions take this extremely simple form. So first of all, they only depend. So they only depend on the subgroup of ZQ that stabilizes the fixed point at which our string webs are ending on. So you know, they only depend on the type of singular fiber you have. So for the SU2 and F equals 4 singular fibers, which have Z2 stabilizers, you just get this function. And if you plug in this BPS spectrum of SU2 and F equals 4, and you Taylor expand the functions to second order in the Fi parameters like we did here, then you find indeed that they match this function. Now that's not so surprising maybe, because the BPS spectrum of SU2 and F equals 4, as I'll review in a second, is very simple. But for the Minahan-Nemeshensky theories, you also get functions that look like this. And that is very surprising because the BPS spectra of these theories are very complicated. So another interesting fact is this is for the E7 theory and this is for the E8 theory. You get these relationships between these four different theories. So the E7 spectrum, this function, this term here is a specialization of the SU2 and F equals 4 function, where you set two of the variables equal to each other. And similarly for the E6 function, you combine the SU2 and F equals 4 and the E6 Minahan-Nemeshensky functions, and you specialize various variables equal to each other. And the reason for these relationships is because the way the Poisson transformation works is you get certain functions which only contribute to certain singular fibers. So you know any CFTs which can show up as part of the same F theory compactification, you get relationships between them in that way. So the Z6 orbifold has both Z6 fixed points, Z2 fixed points, and Z3 fixed points. And so you get relationships between the BPS spectra associated to those three different types of singular fibers. And similarly, the Z4 orbifold has SU2 and F equals 4 CFTs coexisting with E7 Minahan-Nemeshensky CFTs. And so we get these interesting relationships between their BPS spectra. So that was at first order in perturbation theory, but experimentally motivated by those expressions, we've conjectured some all orders in perturbation theory relationships, where if you take the SU2 and F equals 4 spectrum, specialize these two variables equal to each other, then that's equal to the E7 Minahan-Nemeshensky functions at all orders where you specialize this to 0. And we've tested this against all available data, and it actually, this conjecture does seem to be satisfied. This is the natural extension of that to the E6 theory, which we haven't tested it against any data yet. So I'm less confident about this second one, but it seems natural in light of the first one. Okay, so this is the spectrum of SU2 and F equals 4, just to emphasize why it's not surprising that Taylor expanding these functions gives you some very simple answer. It's because you just get half hypers, so omega is 1, with gauge charge PQ for any primitive P and Q in one of these 3 reps, and vectors with in the singlets of the spin 8 flavor group. So maybe that's not so surprising. But then you look at the E6 Minahan-Nemeshensky spectrum, and here's some data from Hollins and Knightsky, and this table goes on for forever. The representations get arbitrarily complicated very quickly, and even the BPS degeneracies themselves are much more complicated. Whereas before they were just 1 and 2, 1 and minus 2 for SU2 and F equals 4. Here, you know, you have some 44s and 16s and stuff. So the fact that the Taylor expansions of those functions that are constructed out of these BPS spectra are so simple is pretty cool. Okay, so just to summarize, we've derived constraints on the BPS spectra of these field theories for arbitrarily large values of impermittivity. And at leading order in the FI parameters, these constraints are pretty weak, but we have obtained some new BPS state counts. But the formalism will allow you to straightforwardly generalize to higher orders and yield the entire BPS spectra, not just of the CFTs, but of the little string theory also. And perhaps, so the cooler result we have at this order is motivated by this leading order expression. We've conjectured strong all orders relationships between the BPS spectra of the various field theories that coexist within these same F theory compactifications. And yeah, they're satisfied. Okay, and just to stress that we know that these infinite towers of CFT spectra are not the same as the whole little string theory spectrum, that we must be missing some states. You can see that from the wall crossing formula. So if I bring my D3 brain over here, so this string web is clearly a bound state of this string with this string. So if I bring my D3 brain over here, then that string web disappears from the spectrum. But going in the reverse direction, the wall crossing formula tells me that I must get this string web as part of the spectrum. So there's some interesting cancellations that are conspiring so that at first order, none of these string webs contribute to the metric. And it would be interesting to understand where they're coming from, presumably some Fermi zero modes or something. How much time do I have? All right, I'm out of time, so let me skip these two slides. So in conclusion, hyperkähler quotient yields computationally useful explicit analytic expressions for K3 metrics. They secretly encode the problem where the solution to a little string theory BPS state counting problem. And by secretly, I mean via Poisson resummation. So the formulas you get from the hyperkähler quotient look nothing like the GMN functions, but you Poisson resum them and all of a sudden the Bessel functions start showing up and you see the BPS spectrum. And in particular, there are piecewise constant lists of integers hiding inside of K3 metrics. So you have some smooth geometry problem, but they encode these nice integers. And similarly, we find characters of spin 8 and EN representations, and we find an interesting dependence on the geometry of string web. So all of that is encoded inside of K3 metrics. Via string dualities, you can recast this BPS state counting problem in various ways. So one way is in terms of open string reduced Gromov-Witten theory. And that's just saying that you can fatten up the string webs into holomorphic curves in M theory. And this aligns with the SYZ construction of mirror manifolds. So I don't have time to talk about that, but you can read about that in our paper. And then regarding the Coulomb branch construction, by finding the full BPS spectrum of the little string theory, we'll complete the specification of a second equivalent construction of K3 metrics. And we can do so by Poisson resumming the Higgs branch result at all orders. And this is sort of neat because the regime of validity of the Higgs and Coulomb formalisms, they overlap, which is how we are able to compare them, but they're valid in different regimes. So they're different expansion parameters. One is an expansion about the orbifold limit, whereas one is an expansion about the semi-flat limit, where the size of the elliptic fibers is very small compared to the size of the base. And so okay. There are a bunch of other approaches to studying the BPS spectra of this little string theory. Most promising is probably, besides the open Gromov-Witten theory, if you want to directly attack this problem, is geometric engineering of the little string theories. So from that point of view, this is the generalized Donaldson-Thomas theory of some non-compact threefolds. And as I mentioned, even without most of the BPS state counts, the Coulomb branch construction yields some very accurate approximations just by iterating the integral equation once. Some generalizations we're looking to study in future work. If in the Higgs branch construction, adding D6 brains wrapping the T4 or an orbifold thereof will allow us to obtain nearly all, or hopefully all known compact hyperkähler manifolds. So Hilbert schemes of points on T4 and K3, and hopefully also O'Grady's exceptional examples. And 3D mirror symmetry again relates these to little string theories. So again, there's this comparison with some Coulomb branch formalism. We can Poisson resum our formulas 1, 3, or 4 times, not just 2 like we did here. And those probably yield other interesting expansions with corresponding counting problems. And although we focused in this talk on K3 and little string theories, we mentioned in our paper that analogous stories hold for moduli spaces of field theories in various dimensions whose Coulomb branches are non-compact 4-dimensional hyperkähler manifolds. So for example, we get some relations between Higgs branch moduli, Higgs bundle moduli spaces and equivariant Higgs bundles, which are pretty cool. Okay, let me stop there.
Okay, so let's thank Max for this very nice talk. Are there any questions?
Maybe I can ask a question? I'd like to ask the following. Since you started with torus compactification, should I expect that you have SL to Z hidden somewhere in your construction?
Yeah, let me think for a second.
Which torus do you have in mind, Sergey?
Well, in the beginning, there was a compactification of the torus. I don't know, maybe then it disappears somewhere, but...
You mean like back in the heterotic frame, right? We're compactifying 5 branes on a torus.
Yeah, at least in the beginning. Or at some point you had D3 branes, which also, well...
Right.
Duality invariant.
I mean, the torus is sort of, I mean, there clearly is a torus here, but it's not clear what mileage one can get from it, because once one, for example, if I use strong weak duality for SO32 heterotic string theory to turn this into a D5 brane, and then I start T-dualizing, then I break this, I replace the torus by some curved manifold by K3. And so all of the frames where I see, I mean, okay. Yeah, all of the frames where I can think about BPS state counting in some nice way, there isn't really a torus there. So I'm not sure that the generating function should be expected to be modular forms. There probably is some nice way to encode, to write some, there probably are some nice generating functions for the BPS states, but they're probably going to be sections of some more complicated line bundle on some other space. Probably not just modular forms on SL2Z.
Actually, another motivation for this question comes from comparison to what happens in Calabi-Yau compactifications, where exactly the same Poisson resummation which you used, it relates, one can say type 2A formulation to type 2B formulation. And in type 2A formulation, for example, D instantons, they described, well, essentially by these GMN equations, which you use also, but in type 2B, they also arise, but they, how to say, they become explicitly SL to Z covariant. So in other words, Poisson resummation allows to reveal hidden SL to Z. And
here is the is this SL2Z S duality of type 2B string theory though?
Yes, yeah, exactly.
So here we might not have that because we're in little string theory rather than the full string theory. And so, I mean, at least in the heterotic frame, there is no coupling constant that we get to play with anymore. That might be an intuitive way to understand this difference.
Okay, thanks.
But yeah, it's a good question. We've speculated a bit on what sort of generating function ought to be a natural way to encode these BPS spectra. We have some comments on this in our paper that one natural way to think about this is if you compactify further, if you study some K3 fibered threefold, and you have a D3 brane wrapping a particular 3 cycle in this compactification, then the superpotential of that D3 brane gets contributions from the same world sheet instantons that contribute to the metric here. And so that superpotential might provide a natural generating function for encoding these BPS states, but that superpotential will be a section of some line bundle on some more complicated moduli space. So that wouldn't, yeah, I wouldn't expect it to be SL2Z covariant.
Okay.
Okay, I wanted to make one comment on the first part of your talk. Is it fair to say that this Coulomb range construction is literally the same as the construction by Kontsevich and Zauberman of metrics on SYK vibrations using networks?
Yeah, good. It's very closely related. So they construct the problem they were interested in. First of all, there weren't metrics involved. They were just looking at K3 surfaces as complex manifolds. So they were just interested in all right, let me say the problem they were interested in. Say I give you K3 with some counts of these string webs. Then can I build up the mirror K3 surface as a complex manifold? And the way that they went about doing this was they constructed the sheaf of holomorphic functions on each open set. In their case, they were working in some sort of formal algebraic ways. So these open sets really had size 0. So there was no analytic discussion of convergence or anything.
So they were working near this maximal degeneration corresponding to the semi-flat metric as well. I think.
So this was studied by Gross and Wilson, but there are no metrics in the Kontsevich-Soibelman paper. But from the point of view of the Guido-Mornitsky formalism, the sheaf of holomorphic functions is given by these x's, and the gluing that Kontsevich and Soibelman studied, where they glued together the groups of holomorphic functions on these various open sets. That's just these discontinuities that Guido-Mornitsky study.
Right.
So yeah, their formalism is very strongly motivated by that Kontsevich-Soibelman paper. It's sort of cute historically how this worked, because the first place where the symplectomorphisms that show up in the Kontsevich-Soibelman wall crossing formula first showed up was in this Kontsevich-Soibelman paper, which was studying this problem of building K3 surfaces up as complex manifolds. And so then they realized that these symplectomorphisms could be used to formulate this more general wall crossing formula. But now we're relating it back to the geometry of K3 surfaces in this way.
Okay.
Okay, any other questions? So if not, let's thank Max again for his very nice talk.
Thanks again
And-
for the invitation.
Yeah, you're welcome. And so thanks very much to all the speakers, and we'll resume again tomorrow morning at 9 o'clock Lisbon time. Thanks, and bye-bye.